Thank you very much for the introduction, Marianne, and thanks to all of the organizers for, well, inviting me personally here, but more importantly, organizing this fantastic school in this wonderful location. I realized that with the mountains calling, it's hard to stay focused on this stuff, so I'll try to, instead of showing lots of PowerPoint slides, to improvise this a bit. And I also hope that people feel very free to interrupt me. I actually intentionally did not prepare 6 hours worth of me speaking for over the next 3 days. So I hope people interrupt and we have a discussion about these topics. So let me just very briefly say what my qualifications for giving these talks are, other than the fact that I've developed a little bit of gray hair, and it looks like the people who have a bit of gray hair are the ones who get to stand in front by the rules of this. So my name is Ilya Mandel, as you've heard. I started out doing general relativity. I realized very quickly that A, I probably wasn't quite clever enough to do it, and B, I have since forgotten most of it. Then I spent quite a few years doing data analysis, including as a member of the LIGO collaboration. So I was a member of LIGO for about 10 years, focusing primarily, though not exclusively, on issues related to compact binary coalescence searches and particularly parameter estimation. This stuff I still somewhat remember, so although you have experts like Alan in the audience, if other issues come up, feel free to ask me questions. And then I sort of gradually transitioned into trying to understand what the next steps might be in this endeavor of gravitational wave astronomy. Amazing people build fantastic instruments that you've already heard about from people like Peter. Then people have spent a lot of time figuring out how to search for these sources, so you've heard about that from Alan. People have spent time figuring out how to analyze these sources and extract their parameters, and you'll hear about this from people like Neil Cornish, who I think will be here next week, and others, of course. But in the end, okay, it's great. We've figured out that there are some sources we have seen already, plenty more we will see, we will measure their parameters. What do we actually learn? And in order to understand what we can actually learn, typically we want to have some models for what the universe is like and how the universe creates these sources for our gravitational wave detectors. And then we can use our observations to constrain those models and therefore learn something about the universe. So a few years ago, I started building these models with the idea of combining my interest in astrophysics with some knowledge of statistics to try to create a kind of framework for pulling together astrophysical modeling of the sources of gravitational waves, particularly compact binary sources, with the astrostatistics techniques necessary to interpret the observations in view of those models. And so that's what I mostly work on these days. I also do some other work on astrostatistics, which I probably won't be talking about here. And I also do some work on trying to understand the electromagnetic counterparts of gravitational wave sources, which is something I might talk about if time permits, as well as a few other things in theoretical astrophysics like tidal disruption events, dynamics of dense stellar environments, and so on. But as I said, we'll start by talking about models and trying to understand where these gravitational wave sources, particularly compact binary sources we've seen so far, come from. And actually the first place where I will start is trying to convince you that there is absolutely no way we should be ever seeing any merging compact binaries. They just shouldn't exist. And then I will try to argue why, in fact, this first order view that they shouldn't exist should be corrected by a second order view, which is that they may exist but should be quite rare and require some exceptional rare channels of stellar and binary evolution to form, and therefore observing them will allow us to probe those rare channels. So why don't they exist? Well, they don't exist because of a separation problem. And the separation problem, briefly stated, is stars are big, gravitational waves are weak, okay, except at small separations. Okay, so first of all, what I mean by stars are big. So do people know how big the sun is? I know how big the sun is. The sun is 1 solar radius. It's about 100 Earth radii. That's right. So actually the density of the sun and the density of Jupiter and the density of the Earth are pretty much the same within a factor of few, which is kind of surprising. So the sun is about 1,000,000 times more massive than the Earth, which makes it about 100 times larger in radius. But okay, let's suppose I actually wanted to figure out what a solar radius was in some more sensible units, and I wasn't sure that it was the density of the sun was about the same as that of the Earth. You can try to approach it that way by trying to actually think about hydrostatic equilibrium within a star, but then you have to know something about nuclear reactions that power the star, and it's a slightly non-trivial calculation that requires a few other assumptions. So maybe instead we can just calculate it very simply based on the fact that, well, the sun is roughly a black body, and the Earth is roughly a black body, and the Earth is roughly in thermal equilibrium because whatever luminosity comes in from the sun must ultimately be radiated by the Earth as a black body. So that means the luminosity of the sun is proportional to radius of the sun squared times temperature of the sun to the 4th power. Luminosity of the Earth is proportional to radius of the Earth squared times temperature of the Earth to the 4th power, right? Surface area times temperature to the 4th. And then we realize that the part of the luminosity, the fraction of the solar luminosity that actually hits the Earth, right? So we're going to call this L Earth in, looks like something like L sun times, okay, the fraction of the solid angle that's made up by the disk of the Earth as viewed from the sun. And so this is something like radius of the Earth squared divided by an astronomical unit squared, right? So if you consider the circumference of a spherical surface as 1 AU from the sun, how much of that does the Earth make up? Well, I'm ignoring factors of 2 and pi everywhere, and I will continue to ignore factors of 2 and pi for pretty much the duration of my lectures. So it's all going to be back of the envelope stuff. This is, well, back of the board. So therefore, bear with me and forgive me for ignoring things like 4 pi. They are important if you want to get exactly correct answers. If we want to get, of course, if you want to get exactly correct answers, you also, when doing this calculation, you have to worry about the Earth's albedo, for example, and other things of that sort, which I'm going to ignore. So for my purposes, good enough. We'll get an answer to within, at most a factor of 2 of being right this way. Okay, so now, if I equate these two by saying that the Earth is in thermal equilibrium, and I plug in for L sun, this expression of R sun squared times T sun to the 4th power, what I find is R Earth squared T Earth to the 4th power is equal to R sun squared T sun to the 4th power times R Earth squared divided by AU squared. Okay, the R Earth squared cancels, and I've done something very wrong. I've canceled the wrong thing. Please forgive me. And so what I now find is that the temperature of the sun to the 4th power is equal to an AU squared divided by an R sun squared times temperature of the Earth to the 4th power. That's not what I want. Why am I writing it this way? What I actually want is the radius of the sun. So what I really wanted to say was radius of the sun squared is equal to temperature of sun to the fourth divided by temperature of earth to the fourth times AU squared, or our sun divided by an AU is temperature of the sun divided by temperature to the earth quantity squared. The temperature of the earth is about 300 degrees Kelvin. Temperature of the sun is about 6,000 degrees Kelvin. It's yellow, so give or take it's 6,000 degrees Kelvin. And so that's about a factor of 20. So factor of 20 squared gives me something like 400. Okay, now if I did this carefully and put in all of my factors of 2 pi, I would actually have found out that it's really about 200. But sorry, what did I write? Did I write it backwards in the end? I did write it backwards. Of course I wrote it backwards. I'm so sorry. All right. Let me fix this because this is embarrassing. Apparently basic arithmetic is not something I can do today. Okay. The radius of the sun had better be less than an astronomical unit, not greater than an astronomical unit. It's an important constraint. I apologize. So you would find this is 1 over 400. I'm claiming it's actually more like 1 over 200 in practice. So the solar radius is about 1/200th of an astronomical unit, right? So that factor of 2 just comes because we've ignored some pi's and 2's. And so it's about 1/200th of an astronomical unit. So an AU is about 150 million kilometers. So the radius of the sun is about 700,000 kilometers. A million kilometers for good measure is good enough for our purposes. So why is that a problem? Well, suppose for a moment that the sun could actually make a black hole. It can't. It's not massive enough, but suppose it could. If it made a black hole, it wouldn't quite make a black hole with the entire mass of the sun, though, because usually what happens, even if you consider much more massive stars, they fuse hydrogen to helium, and then helium into carbon and oxygen, and carbon and oxygen to neon and magnesium, and ultimately all the way up to iron in their cores, but their cores end up making up typically something like 1/3 of the mass of the star. The rest of the mass, some of it is ejected altogether. Massive stars have strong winds, so a lot of the mass is ejected in winds, but even the mass that isn't ejected, you just end up with outer shells of hydrogen and helium and so on, which are not processed into the higher atomic number materials. So you only at best end up converting something like 1/3 of the mass of the star into a core that can collapse into a compact object like a neutron star or a black hole. This is why, in order to make a neutron star, which is, let's say, canonical mass of a neutron star is about 1.4 solar masses, you need to start actually with a star that's about 8 solar masses, maybe 7 under some circumstances. If you want to make a black hole, where, as far as we know, black holes have masses of 5 solar masses and up, you actually need to start with a star with a mass of about 20 solar masses or higher. You don't convert the entire mass of the star into the compact object, only a small fraction of it. So let's ask the following question. So suppose we just started with a binary with 2 suns, right? And since we know this radius of the sun, and we waited for a while, and let's imagine that our suns made black holes in place without, we're not going to worry about the fact that actually there is some mass being lost from the binary through winds, for example, and mass loss tends to widen the binary and brings things further apart. We'll ignore all of those complications. We'll just imagine that you started with 2 suns in a binary orbit. Now, the radius of the binary orbit had better be at least a few times the radius of the sun. Otherwise, you're in trouble, because then you just immediately, when you put these 2 stars there, right, if they're, touching already or in contact already, then okay, you end up with 1 star. That's wonderful. It's exciting. Stars do merge. It's pretty, but it doesn't form two compact objects that can be considered distinctly as distinct merging compact objects that LIGO can detect. So we don't want to go there. So we're going to consider two black holes that are each 1/3 of a solar mass and are separated by, let's say, at least 3 solar radii. And now we will ask the following question. How long will it take these two guys to merge through the emission of gravitational waves? So I should apologize in advance because, of course, I don't know exactly what was covered in all of the lectures so far, and I might repeat some of the material that has been covered, and other people might repeat some of the things that I'm talking about. So Chris Belczynski, for example, I think is talking next week, and he will talk about stellar and binary evolution as well. I think it's probably okay because, and of course, some of you may already know a lot of this stuff, and people have different expertise in the audience. I hope it's all right that there's going to be a fair bit of repetition because hopefully all of us have slightly different views on these things and explain them in slightly different ways. So hopefully it's okay. But if I start really, going through some calculation that's completely identical to something somebody did yesterday, which I'm not aware of, then please do feel free to stop me. I don't want to bore everybody and waste everybody's time. Okay, so let's actually ask the question, okay, how do we estimate, again, back of the envelope, how long would it take these two sources to merge? So is this a calculation that people have done already? No. All right, so let's start with that. So I presume people have talked about gravitational waves sort of in a back of the envelope sense and have written down a quarter-pole formula, right? So people have written down something like the following. I probably need to erase some of this stuff. Yes. Fantastic. Oh, you already gave the chirp time formula. All right, fine. I'll derive it, and fantastic. And hopefully I'll get an answer at least vaguely similar to what Alan gave you. One of the things I find most exciting about doing back of the envelope physics is that 90% of the time I find I'm reinventing the wheel, but sometimes my wheel comes out circular and not triangular, and I feel so good about myself. It's so much more fun than just looking it up in Alan's beautiful notes and finding out what the answer should be, which of course is correct, but instead trying to do it and then finding it's roughly right. It's so exciting. Anyway, okay, so this part I'm not going to derive, but people have probably seen already that H, the gravitational wave strain, looks like Q double dot, where Q is the mass quarter-pole moment, and the dots are time derivatives divided by R, which I'm just going to write as Q frequency squared divided by R, because if I have something that is oscillating, so that means I'm basically multiplying, Q in this case has a sort of, e to the 2 pi I of t term, and taking a time derivative brings down a factor of f, or a factor of 2 pi f, and I'm ignoring my 2 pi's. By the way, presumably people have talked about why it has to be Q double dot. It's because, of course, something has to be changing. Cannot change mass because of conservation of mass. You cannot have a time-varying dipole moment, unlike you do in electromagnetism, right? We all know that that's how an antenna works, is because you have a time-varying dipole moment. But because masses are all positive, a time-varying dipole moment would actually correspond to a time-varying linear momentum of a closed system. Cannot have that because of conservation of momentum. Cannot have at first order time-varying spin because that corresponds to a non-conservation of angular momentum. So the first thing you actually can vary in time without violating conservation laws is a mass quarter-pole moment. And you know that the wave has to have a 1 over r behavior. And the last thing you know is somehow dimensions have to match up. Now, in units of g equals c equals 1, which probably people have already mentioned, the dimensions of time, mass, and length are the same. So Q, which is a mass quarter pole moment, that's a mass times the distance squared, so that's like mass cubed. R is like mass. I want to get a dimensionless thing out, so that tells me I have to take two time derivatives. I don't have to have some time derivatives, because if there's nothing varying in time, then I shouldn't be able to get any information and any energy out of the system. So I know I need to have some time derivatives, and I better have two in order to get a dimensionless quantity, right? Q is mass cubed, R is mass, so this on its own without any dots gives me mass squared, so I need to have two dots because each dot gives me a frequency. Frequency is 1 over time, so 1 over mass. So this way, H is really a dimensionless number. The next thing okay, this one I'm not going to derive, take it on faith in some ways, although you can justify it by doing an analogy with, let's say, any kind of a scalar field like an electric potential, that the flux you're going to get out when you have a time-varying scalar field, the flux through a surface goes as h squared times f squared. And so the total luminosity, in other words, the total rate of energy change, d dt in gravitational waves, is going to go as h squared. Well, it's not just proportional. It's basically equal to up to my, factors of 2 and pi that I'm ignoring. It's h squared f squared times r squared. Or, in my notation, q squared f to the fourth, which, remembering that q is mr squared or ma squared, where a is the binary separation. People often use this a because it stands for the same major axis. We're going to, for the purpose of this calculation, restrict ourselves to circular binaries, but just to avoid any confusion between r for the distance to the source and the separation of the binary, I'll write this as m squared a squared what did I mess up? Hold on. Okay. I have h squared, so that's q squared f to the fourth, right? Times f squared. Thank you. Thank you. I'm sorry? And a is also to the fourth. Not my day. All right. Okay. Maybe I should have woken up. Next time I'll try coffee. I don't normally drink coffee, but clearly I'm badly in need of it. Thank you. All right. So I have m squared a to the fourth f to the sixth. Quick check of dimensions, just to make sure that this hasn't gone crazy, because it's the best way. Although, funnily enough, I made a mistake that actually made the dimensions work out. So sometimes dimensions don't fully help. I made two mistakes. But energy, right? Energy is like mc squared, and c is 1, so energy has units of mass. Time has units of mass, so the left-hand side here is actually dimensionless. The right-hand side, mass squared, mass to the fourth is mass to the sixth, times frequency to the sixth, that's 1 over time to the sixth, so 1 over mass to the sixth. So right-hand side is also dimensionless. So dimensions do work out. Okay, the next thing I'm going to say is that this has to be balanced by the amount of energy I'm losing from the binary's orbit. Yes, please. Okay, so let me try to give some intuition for the very dirty intuition for h squared f squared. So if you think about the if you have waves propagating at the speed of light, as you do for both electromagnetic waves and gravitational waves, time derivatives and spatial derivatives basically end up being the same thing. Okay, up to a factor of c, but that's 1 in our units. So that means that the different components of the stress energy tensor are actually comparable, right? So the energy density and the flux are kind of the same thing. So you might, for example, if you remember that the energy density in an electric field goes as E squared, and you remember that the electric field is a gradient or a spatial derivative of the electric potential, it tells you that the energy density, which remember we said is kind of like the local energy flux. So think of it as luminosity per unit area. should go as E squared, where E now is the electric field, which is something like the derivative, whether in time or in frequency doesn't matter, let's call it in frequency, of the electric potential squared. And so, in other words, the total energy change dE by dt looks like the time derivative squared of the potential times r squared, and all I'm doing here is I'm sort of mentally equating one scalar field with another, so that I'm equating the electric potential with this scalar metric perturbation. If you want to do this carefully, okay, what you actually need to do is write down the stress energy tensor, and the stress energy tensor for something like a scalar field is T mu nu is 8 pi phi mu phi nu. See, it helps that I remember just a tiny bit of my GR. This is about as much as I remember, but I remember this much. And so again, you've got these two derivatives, which here, you know, whether it's a time derivative or a spatial derivative doesn't make any difference. Really, because we're talking about the flux, we should have one time and one spatial derivative, but we might as well think of them both as time derivatives. And so they each give me a frequency squared. So I have phi squared frequency squared, except that I'm replacing, in this case, phi by h. So yeah, this part is, I agree, it's not a proof. It's hand wavy because I'm not going to try to properly do GR on the board because I will embarrass myself. Even more than I already have, which is saying quite a bit. Okay, so this is my rate of energy loss in gravitational waves. Now what I want to do is say that, look, where's the energy coming from? Well, it's coming out of the orbit, the Binaries orbit, right? That's the only place it can come out of. So this has to be equal to, up to a sign, dE orbital by dt. Now what's E orbital? Well, E orbital, okay, I'm going to assume that my two masses are the same. You don't have to assume that, but let's suppose the two masses are the same. And I will also not worry about differences between total mass, reduced mass, and so on. My two masses are the same. My total mass is about the same within a factor of 2, which I don't care about. My reduced mass is about the same within a factor of 2, which I don't care about. So my orbital energy is G. Well, my potential orbital energy is gm squared divided by A, where A is, remember, the binaries separation, the same major axis. Now, that's a potential energy. Okay, it actually has a negative sign if I'm being careful about it. Then there's, of course, the kinetic energy. The kinetic energy by the virial theorem is just half of that, but with a positive sign. So plus gm squared over 2a. This is the potential energy, that's the kinetic energy. So the total is minus gm squared over 2a. In fact, minus gm1 m2 over 2a actually is the correct orbital energy, even for eccentric orbits. So by luck, I haven't screwed up this formula too badly with my simplifying assumptions. And if I now take the time derivative of this, okay, my masses aren't changing, right? I just have two masses. Let's say I'm still very far away, essentially in the, just barely post-Newtonian limit. And so my masses are just staying the same. The only thing that's changing is the separation. And so d orbital by dt is equal to g m squared over a squared dA by dt. Right? I didn't screw this one up, right? Ignoring factors of 2. So now I equate these two quantities with each other, and the only other thing I have to use are Kepler's laws, because otherwise I have some things with A's and some things with F's, and that's making my life difficult. So let's substitute something useful for one of them. Let's just do it for, okay, I seem to have more A's this time than F's, so let's replace my F with A. I'm going to erase this. So Kepler's law tells me that omega is equal to root gm over a cubed. So frequency is the same thing within a factor of 2 pi. So that's my, roughly speaking, my frequency. And so I'm going to plug that in. I'm going to ignore g's from now on because g equals c equals 1 anyway. So what I have now is, on the left-hand side is the gravitational wave energy loss. Looks like m squared a to the 4th times this thing to the 6th power, which is m cubed divided by a to the 9th, right? So yes, I think that's correct. And on the right-hand side, I have m squared over a squared dA by dt. Quick unit check. The right-hand side is dimensionless because m and a have the same units and a and t have the same units. The left-hand side, okay, this is mass to the 6th. This is times mass cubed is mass to the 9th divided by mass to the 9th. Okay, that's also dimensionless. Okay, so if I have screwed up, it was in some less obvious way, so maybe it's okay. So this tells me that dA by dt is equal to, all right, so now let's divide this by m squared, so I've got m cubed, and dA by dt, okay, now the a's, okay, here I have 1 over a to the 5th, times a squared is 1 over a to the 3rd. And this tells me what the typical time scale is for gravitational wave merger, because the time scale is given by a divided by dA dt. Of course, you're going to tell me that, look, but dA by dt is changing in time. You cannot just say that you have some constant rate. This would be true if I, a was changing at a constant rate, right? I just take a divided by dA dt, and that tells me what the actual time scale is. But even if it's not exactly right, it's within a factor of a few of being right, typically, so good enough for our purposes. So if I divide a by dA dt, I get something that is proportional to, okay, so dividing a by this, I get m to the minus 3, a to the 4. And this I actually think is right. So the wheel is circular. Okay, so we've computed the gravitational wave time scale, right? It goes as a to the 4th divided by m cubed. Now, if you want to plug in numerical values, and this part won't quite work out because we've ignored we've ignored sort of too many factors of 2 and pi, but just to give you a rough sense of these things, we can actually do this. So in order to do this, what's convenient is to convert masses. We can use sort of either mass units or time units or distance units for everything. And the conversion factor that's very convenient to keep in mind is that a solar mass in units of distance, which is really gm solar divided by c squared. If I really put in g's and c's correctly in this way, I do get something with physical units of distance, is 1.5 kilometers. And if I take this and divide by another factor of c, so write down gm solar divided by c cubed, I get 5 microseconds, so 5 times 10 to the minus 6 seconds. So one solar mass is 1.5 kilometers, is 5 times 10 to the minus 6 seconds. Why is this very useful to know? Well, for example, forget about anything in gravitational waves, right? Let's imagine that you're trying to figure out, let's say you remember somebody was telling you about the Eddington experiment of 1919 to measure the deflection of light by solar eclipse. To measure the deflection of light from a distant star by the sun during a solar eclipse, right? Okay, so you know that the sun, that the distant light could at closest have come to roughly the radius of the sun from the center of the sun. Okay, if it gets any closer, the light actually goes into the sun. Eclipse or not, that light isn't seen again. So that's the closest it could have come, and you want to know what is the angle by which that light could have been bent, right? Well, it's very simple, because the angle by which that light could have been bent is, well, you know that probably that bending angle, even if you don't remember any GR, should be larger if you have a more massive object, right? A more massive object bends things more strongly, and it should be smaller if you're further away, because, okay, if I'm really, really far away from the sun, it's clearly not going to do any significant bending of the light. So it stands to reason that in dimensionless units, because an angle is dimensionless, it should go like solar mass divided by the distance of closest approach. So it's solar mass divided by solar radius. Now I know that a solar mass, of course that should be G's and C's, but since I remember that a solar mass is 1.5 kilometers, all I have to say is, okay, that's about 1 kilometer. The solar radius is about 1 million kilometers, so I expect the bending of light by 1 part in 10 to the 6. And it's certainly correct within a factor of 10. Meaning that, okay, I can at least estimate, you know, was it conceivable that Eddington in 1919, using the technology of the day, could have made this measurement? The answer is yes, because we're talking about sort of an arc-second level measurement. We're not talking about a micro arc-second, which you might have said is ridiculous and unfeasible. We're also not talking about 20 degrees, which maybe would have led you to ask how come people haven't noticed it before, because people have been observing stars for quite a while before Eddington, right? So it's not too crazy that the answer turns out to be 1 arc-second, right? 1 arc-second is about 5 times 10 to the minus 6 of a radian. So give or take, it's arc-second level measurements, right? And all I have to do to figure that out is to know that a solar mass is 1.5 kilometers. So just a useful number to remember. Okay, so now if I plug this into here, for my problem, right? So for my problem, the gravitational wave timescale. Okay, so mass. Okay, we're talking about, okay, a third of a solar mass. So that means 3 cubed m sun cubed, because this goes as m to the minus 3 times a to the 4th. Okay, I said 3 solar radii, so that's 3 to the 4th solar radii to the 4th. Now, what did I write over here? This should have been to the minus 3. I'm sorry. Okay, so now I remember that now I have all I have to do is plug things in my funky units. I'm going to measure time for a moment in kilometers, and then I will just use the speed of light to convert this into seconds. So if I put reasonable numbers in, okay, 3 cubed times 3 to the 4th, okay, so 3 cubed is 30, 3 to the 4th is 80, 30 times 80, for good measure, I'll say it's 1,000. Not quite right, but close enough. So I've got 1,000. Now our sun, okay, I'm going to use 1,000,000 kilometers for the radius of the sun. So this is times 10 to the 24 kilometers to the 4th power. So it was a third to the minus 3, so it is 3 cubed. Here I did screw up. Here I think I didn't. but you're very, thank you for checking, because I can easily mess up. Okay, and the solar mass, okay, we said that it's 1.5 kilometers. I'm just going to round it to 1 kilometer. I'm ignoring so many factors of 2 and pi. I will have to tell you in the end what the actual answer is for this, so I'm slightly approximating, but at least to get the right ballpark, right? So, you know, are we talking about seconds here? Are we talking about 10 to the 50th years, right? So let's at least see if we can get right ballpark here. So the solar mass is roughly 1 kilometer, so times 10 to the minus 3 kilometers. Okay, so now this is 10 to the 3, 10 to the minus 3, sorry, times kilometer to the minus 3. Thank you. Sorry. Times kilometer to the minus 3. So I have 10 to the 27 kilometers. Now I really like this in seconds. So I remember the speed of light as 3 times 10 to the 5 kilometers per second. So I divide this by 3 times 10 to the 5 kilometers per second to get seconds. So I get 3 times 10 to the 21 seconds. Now remember that a year is pi times 10 to the 7 seconds, or about 3 times 10 to the 7 seconds. So I convert this into years. So I divide this by 3 times 10 to the 7, and I get 10 to the 14 years. And I say, wait a second, I have a problem. It turns out to be a bit less than that, but it actually is correct that it turns out to be longer than the age of the universe. So if I put in the right factors of 2 and pi, I won't quite get 10 to the 14 years. I'll get something like 10 to the 12 years if I remember correctly for these assumptions. But so I am off by 1 or 2 orders of magnitude here, but I'm not off by 10 orders of magnitude, right? I really have a problem. This is bigger than age of universe. So what have we learned? We learned that if we take 2 suns and let them form 2 black holes in place and just wait for gravitational waves to bring them together, they will, but it will take longer than the age of the universe. And then if I can make matters even worse by remembering a little bit of astrophysics. And the astrophysics I'm going to remember is that what really happens during stellar evolution is that first the stars sit in the so-called main sequence, where they are burning hydrogen, fusing hydrogen. Okay, burning in this case doesn't refer to an oxidation reaction, it refers to fusion, right? So hydrogen is being fused to make helium. That's happening in the core. The star during this main sequence will change a little bit. It will expand typically by a factor of a few, about a factor of 5 in radius over the main sequence. That's already a bit of a problem, but for us. But it's still roughly the same size as it started. But then something happens when the star runs out of hydrogen in the core. When in the core, in the center of the sun, or the star where all of the fusion is happening, all of the hydrogen is converted to helium. There is a sudden drop in pressure because you are no longer having this thermal and radiation pressure support, and that means there is a contraction. In this contraction, of the core, in this contraction, the gravitational binding energy is released. There's a sort of teeter-totter effect, and this energy goes into the envelope of the star, and the envelope begins to expand. And the envelope expands very, very significantly by something like a couple of orders of magnitude. So our sun, for example, will become a red giant with a radius roughly that of 1 AU, right? So it will reach out to roughly the size of the Earth's orbit. So why is this a problem? Well, it actually means that I couldn't put the 2 stars at just my 2 suns at a separation of 3 solar radii from each other. If I did that, well, they would have actually merged late in the main sequence. Okay, maybe I put them at 10 solar radii or 15 solar radii from each other. Okay, they avoid a main sequence merger, but at some point during their evolution, as they begin to expand, as they turn into giants, they're going to get much, much larger than the separation, and inevitably they will merge. They will start transferring mass to each other. They will do all kinds of fun stuff, but at 0th order, it seems like, well, this is not going to be a source of gravitational waves. You will just have, okay, you take 2 big giants and they merge, and you end up maybe with 1 big giant that has twice the mass. Fantastic. Maybe eventually it will collapse into a neutron star or a black hole, but you don't have 2 compact objects spiraling together and emitting gravitational waves of the kind that LIGO and Virgo like to detect. So I would really need to place my 2 suns not 3 solar radii apart, but 3 astronomical units apart. And if I do that, then because this gravitational wave merger timescale scales as a to the 4th, if I put them another factor of 100 further apart, that means the gravitational wave merger timescale goes up by a factor of 10 to the 8. So now we're talking about 10 to the 20 years or more. These things will never merge. And you might ask, well, okay, can I play with things, maybe more massive stars things aren't so much of a problem for them. Turns out it doesn't help, because on the main sequence, for example, for things more massive than the sun, the radius of the star, roughly speaking, is the radius of the sun times the mass of the star in units of solar masses to the 0.6 power. It's about 0.8 for things less massive than the sun, about 0.6 for things more massive than the sun. So if this is what's setting my minimal separation, because I don't want the two stars to touch, then I still end up with m to the minus 3 here, and I have 0.6 to the 4th power, which is 2.4 here. And so yes, the gravitational wave timescale can shrink a little bit if I go up in mass, but not by enough. So I still have the same problem even if I start with two stars that are 100 solar masses each, as if I start with two stars that are 1 solar mass each, right? So even if I start with two very massive stars, I cannot, especially if I consider the fact that they will expand significantly, which, as I said, gives me the fact that they're expanding by a factor of 100 gives me like another factor of 10 to the 8 in the merger time scale. I'm not going to be able to get those two stars to merge in the age of the universe, or those two compact objects to merge in the age of the universe. So that's a problem with gravitational wave astronomy. You can think of it as a kind of fundamental theorem that it's really hard to get sources, compact object binaries, to merge in the age of the universe. So now that we've highlighted the problem, it's probably time to think about how we might try to go about solving it. And I should also say that for people who are interested in this kind of stuff, there is, so my friend and colleague Alison Farmer and I have written a review that roughly parallels some of the discussion I'm going to try to lead here for the next few days. So it appeared in the archive. I don't remember the archive number, but if you look up Mandel and Farmer, it was in June of this year, so it's a few weeks old. And so if you do want to see a couple of prettier pictures that don't hand wave quite so much, but actually show you, for example, exactly by how much a star of a given radius expands, and exactly how close together they have to be in order to merge in the age of the universe, and these sorts of things in more careful calculations, you can go and look it up in that review. Okay, so now let's talk about some of the possible ways you could get around this problem. And I'm not going to talk about some of the ideas that have been suggested by colleagues in cosmology with, let's say, cosmologically formed primordial black holes from some kind of, collapses from some kind of density perturbations in the early universe and so on. I'm going to restrict myself to objects of stellar origin, and in particular to a picture where you really do have two stars that each form one compact object, and those two compact objects come together. There's been also a suggestion, which I think is rather implausible, but we won't discuss it in any detail here, that it might be possible for a single star during its collapse to have a core that sort of splits into two different compact objects, two different black holes. So Avi Loeb had proposed this, and he and a postdoc of his had written a couple of papers on this. There are problems with this approach, I think, that are sufficiently severe that it's not really worth discussing in any detail. So let's just think of two stars. Each star is going to form a compact object. Those two compact objects will eventually merge. Yes, of course. Well, the mass, and so, okay, if you really have an extreme mass ratio case, then the mass in the quadrupole moment is actually the mass of the small object, right? So because you have, I mean, if I have, a speck of dust orbiting around a supermassive black hole, right, my mass quadrupole moment is of course just set by the speck of dust, but the frequency, because of Kepler's law, is set by the mass of the more massive object. So we absolutely could have done it, a little bit more carefully by including the small object mass and the large object mass. Actually, if you do that, the chirp mass comes out very naturally as well, even doing this kind of back-of-the-envelope calculation. So this was just a, we chose some approximations to ignore worrying about these masses. Oh, absolutely, right. You still have the same problem. You actually, the problem is least bad for equal masses. It gets worse if you go to more extreme masses. Basically, if you have very extreme masses, the gravitational, the merger time scale, if you wish, is increased by the inverse of the mass ratio, because really, if you think about sort of this extreme mass ratio problem, right? You're spiraling in very slowly. That's why, for instance, extreme mass ratio in spirals with LISA or intermediate mass ratio in spirals with LIGO are very good tests of strong field gravity. You've got this small object that's spending a lot of cycles in the strong field, right? For comparable mass sources, right? You just zoom in, right? It only takes you a few orbits to go from, let's say, r equals 7m to r equals 6m, right? But if you have a binary with a mass ratio of 1,000,000 to 1, it will take you millions of orbits to go from r equals 7m to r equals 6m, which means that you end up with this very precise signature of the space-time in your gravitational waveform. So there's a theorem due to Finton-Ryan that basically said that, okay, at least in principle, if you have a sufficiently sensitive detector, you can explore the full structure of the space-time with the gravitational waves from an extreme mass ratio in spiral. And so that's why they're very good, for instance, for doing things like tests of general relativity. You can say, okay, is my black hole really a Kerr black hole, or does it have some additional mass multiple moments and so on? But that's an aside. The point is that in terms of the time scale, things get worse. So it's even more of a problem. Yes. I'm afraid I don't. Please share it. Oh, do you want Bathrodicy? Yes, of course. Yes. So indeed. So Stirl described this, study of the space-time of a black hole that you can do so well with extreme mass ratio in spirals as Bathrodicy. Having sort of taken up, as far as I understand, a Greek dictionary and decided that a black hole is Bothros. Apparently, in modern Greek, Bothros has different connotations. If you have a sufficiently dirty imagination, you can probably figure out what it might refer to. So I won't say it out loud, but let's just say that Stirl is no longer advocating for the use of Bathrodicy. I don't know if you have more insight on this. Okay. All right, so that was a good break from our discussion. So we've talked about the problem. Okay, so now let's talk about the solutions. And I'm going to warn you up front, the solutions appear to be fine-tuned, but it's kind of okay up to a point to fine-tune things, because we are, after all, talking about rare events. So how rare? Well, here it might be worthwhile to very quickly remind ourselves of what LIGO and Virgo have seen to date. I know you've already had plenty of reminders of this. Again, just a very quick summary, because we all focus on slightly different features of the events. So far, there have been 6 binary black hole events announced between the 01 and 02 runs, and 1 BNS event. LIGO Virgo members in the audience will say that there are 5.9 BBH events. Not being a LIGO Virgo member anymore, I'm allowed to be a little bit, let's say, more provocative, and I'm going to just claim that there are 6 events, because I'm quite convinced that they're all real astrophysical events. And the 6 events basically range, for the binary black holes, range in masses from about 10 plus 10 solar masses up to about 30 plus 30 solar masses in something that looks like a roughly flattish distribution, let's say in total observed mass. That doesn't mean the intrinsic distribution is flat, right? So this is one thing that's important to appreciate. LIGO and Virgo have strong selection effects on mass. The selection effect, if you think about low masses, so this is just a little aside, but it might be worth remembering this. So if you think about low masses and you think about what does H scale with, okay, we've said before that H goes as Q F squared. You can write down the frequency domain waveform H tilde of F, and I'm not going to bother doing that because I'm sure people have done this already, or if not, I'll leave this to somebody else. But you will convince yourself that during the in-spiral, H tilde of F scales as F to the minus 7.6 times the chirp mass to the 5.6. Okay, that's only true during the in-spiral, not during the merging ring down. So for very heavy events where really the gravitational wave signal-to-noise ratio is dominated by the merging ring down, what I'm going to say doesn't quite work. But let's just pretend for a second it does. So this basically tells you the strength of the signal goes as mass to the 5.6 power. That means the distance to which you can see it also goes as mass to the 5.6 power, which means the volume, which goes as the maximum distance to which you can see it cubed, goes as mass to the 5.6 power cubed, or mass to the 2.5 power. Now, some of you may be aware of the fact that the initial mass distribution of stars, so this is called the initial mass function, IMF, stands for initial mass function. So the number of stars per unit mass scales as something like mass to the minus 2.5 power. Okay, maybe it's minus m to the minus 2.35 or minus 2.3, depending on whether you like the Krupa initial mass function or Salpeter initial mass function, or it's roughly m to the minus 2.5 power. And so one thing you might notice from this is, once you convolve, if you believed, and this isn't certainly not exactly true, but if you believe that roughly the black hole mass function, even in merging binaries, follows the initial mass function, it doesn't, but it's also not orders of magnitude away. And you believe that these are roughly the selection effects, and they aren't quite, because at some point you are dominated by the merging ring down, where the scaling no longer applies. At some point you're dominated by cosmological corrections, which shift the frequency, for example, of the gravitational waves because of cosmological redshifting. And again, that wreaks havoc with the scaling. But if you roughly imagine it's something like this, you multiply these two together, and you find that there's no mass dependence in your selected sample. So perhaps it's not so insane that the observations we have actually appear to be roughly flatly distributed in mass. Sure, but actually the initial mass function we can constrain reasonably well. So the initial mass function, you're absolutely right that we don't know why it has that behavior. That's a very interesting question, why the initial mass function is what it is. Why the binarity fraction in stars is what it is, because most stars are born in binaries and many are born in triples, quadruples, etc. So we can chat about all of those things, but observationally there is very little evidence, surprisingly little evidence, of a departure from universality. So there have been arguments and that say that, oh, in this particular galaxy or in this particular star forming region or in this particular type of galaxy, the initial mass function departs from this simple power law at higher masses, which is roughly m to the minus 2.3 or m to the minus 2.35, and almost none of those have been borne out observationally, or at most when they have it sort of within 1 or 1.5 sigma of this power law. So it really does seem that the IMF is fairly robust. I think what you're right to point to is that, of course, the IMF having that slope doesn't mean that your black holes in merging binaries will have that slope, because there are lots of special things that have to happen to get those black holes to merge, and we'll talk about some of them. And that means that it doesn't, you have other astrophysical selection effects. I'm just saying, if you imagine that the black holes follow roughly the same mass distribution, then, and you convolve it with roughly this selection effect, you might expect something that is roughly flat. And so far, I'd say there is, of course, we'll see. I know that the LIGO Virgo folks are preparing a catalog of their all of their O1 and O2 events, and probably they will analyze what the mass distribution is, and maybe they will start seeing some evidence from a departure for this. But so far, I'd say there hasn't really been any evidence for a departure from a flat observed distribution over something like this range in masses. Yes?
What's precisely the range of masses you're talking about? Because at some point one would have some sort of mass gaps, right?
Absolutely. So you have, so I would say that in general, there are two possible mass gaps around black hole masses, even if you ignore what happens in binary evolution. One possible mass gap, which may or may not be there, is a mass gap between neutron star masses and black hole masses. This presumably would be due to the details of the explosion. So you expect that there is a continuous distribution of core masses before a supernova. There's no reason for that to have any abrupt gaps. But at some point, you may have, things with a mass below a certain mass may have very strong explosions where a large fraction of the material, including parts of the core, are blown away, and you end up with only a relatively low mass remnant. You might have a 3 solar mass core or 4 solar mass core and still end up with a 1.4 solar mass neutron star. And then maybe something happens, and when you have a slightly more massive core, let's say a 5 or 6 solar mass core, it collapses almost in its entirety into a black hole, or at least the explosion is fairly weak. There is some evidence for this from supernova modeling, although it actually seems that it's not quite that clear of a distinction, that there's a range of stellar masses and core masses which are low enough where you definitely just end up with a big supernova explosion and only a neutron star left behind. There's a range at very high masses where you definitely end up with a black hole, and in between you might end up with a neutron star, you might end up with a black hole. It's almost up to numerical noise in your simulations, and maybe that's not a statement about simulations, maybe it's a statement about nature, that even in nature there is some stochasticity in the way that some of the instabilities that actually drive a supernova explosion develop, and those instabilities determine whether you end up, even for almost the same mass, with a neutron star or a black hole. I presume there will be people who might be much more qualified than me to talk about the supernova simulations, so I will leave this to them. I can tell you a little bit about the observational evidence. So it's certainly true that if you look at neutron stars, as far as we know, there are no neutron stars in the universe that are more massive than about 2 solar masses, maybe just a tiny bit over 2 solar masses, right? So the way you convincingly measure masses is typically through some kind of a dynamical mass measurement. So you want a binary, and in this binary you can measure its period, its orbital velocity perhaps, if you're seeing some kind of a Doppler shift induced by the orbital motion, and if you know the binary's inclination. Those 3 things allow you to solve for the masses. In some cases you have additional information. So for example, if the binary is oriented in such a way that you're looking at it edge on, you may be in a situation where the light or other electromagnetic emission from one of the components of the binary passes by the other component, and then you have additional gravitational relativistic effects. So for example, time delays due to light passing in the presence of a massive companion. So that might allow you to measure things more accurately. But these kinds of measurements allow you to, and this works for both neutron stars and similar things in principle work for black hole binaries. They allow you to make measurements of the masses. So for neutron stars, we know of neutron stars that are up to about 2 solar masses. For black holes, we only convincingly know of things going down to about 5 solar masses. So there were a couple of papers in the early 2010s, one by Ferial Ozal et al., one by Will Farr et al. That I was a collaborator on, and we all argued for the presence of a mass gap. It's not completely obvious that there is one because, I mean, right now I'm actually in the process of writing a paper with some colleagues who are doing microlensing observations. And there doesn't seem to be, these are preliminary statements because the paper isn't quite finished yet, but we don't actually see strong evidence for a mass gap there. Now, there could be other issues involved because in microlensing it turns out that if you have a very tight binary neutron star system, for example, you cannot tell it apart from a single object. As a lens, it just looks like, you know, one object, and so that means that you might have 2 neutron stars in a binary, 1.5 solar masses each, total mass of 3 solar masses, and you say, oh look, there's an object in my mass gap. It's a 3 solar mass object, right? So we don't know whether it's really a 3 solar mass black hole or a 3 solar mass neutron star binary. So there are complications, but in principle, there may be a mass gap there. The second mass gap you might see is due to something called pair instability supernova or pulsational pair instability supernova. So the basic idea there is that if your star gets really, really hot, which only happens for very massive stars, you're talking about stars with a helium core that's larger than about 60 solar masses, 50 or 60 solar masses. So that probably means your initial mass was, for these stars, was likely, you know, 150, 200 solar masses. If you have these kinds of, or you had a low enough metallicity, you might be able to do it with sort of a 100 solar mass star, but a sufficiently low metallicity. But if you have these very massive stars there, A, they get to be very hot, B, they are almost exclusively radiation pressure supported during their later stages of evolution. That can create a problem because your radiation pressure, in this case, right, these are very high energy photons, and if they get hot enough, you can get pair production. Your photons break up into electrons and positrons. And when they do that, your radiation pressure drops like a rock. And when it does this, your star begins to rapidly contract, and you create a shock, and that shock can power an explosion, and according to models by people like Stan Woosley, that explosion can completely destroy the star. So there may be a range of stellar masses where you just completely destroy the star. If stars are even more massive, although we know very little about their observationally about the evolution of stars that start out at 300 solar masses, but if such stars, it seems that such stars do exist observationally, and such stars, the idea is that maybe they actually just end up completely collapsing into black holes that are massive enough that the gravity overpowers everything else. But there may be a gap, and that gap may be even slightly exacerbated by the fact that for stars that are not quite massive enough to go through a full-blown pair instability supernova, you might have pulsational pair instabilities where you just have very strong bursts of wind from the star, significant mass ejection from the star. So you might find that your black hole mass distribution really doesn't trace your initial stellar mass function, but ends up actually with a little excess of mass, because let's say things that should have made 60 solar mass black holes are gone, but things that should have made 50 and 55 and 45 solar mass black holes all end up making 40 solar mass black holes because of these pulsational pair instabilities. So now you've got this peak in your distribution at around 40 or 45 solar masses, and then a big gap going until maybe 130 solar masses. Exactly. So this mass ejection is responsible for this peak at around 40 or 45 solar masses. Then you've got this pair instability supernova mass gap continuing to maybe something like 130 solar masses, and then you might have again black holes on the other end of that mass gap. So what that's telling you is that there might be two different gaps. One between neutron-stellar black hole masses, and one above 40, 45 or so solar masses in this distribution. Now, so far, the data are consistent with that picture, but of course, that's one of the things that will be fun to test. In fact, being a betting man, I like making bets on these things. So one of my bets is whether or not you will ever see any objects in the parent stability supernova mass gap. There might be, we'll talk about this, there might be ways to get things there. Yes, please, Alan. Yes, you have. Absolutely, absolutely. So, and of course, we also think we've seen at least one black hole in the other mass gap, because GW 170817 has, we think, has collapsed into a black hole by now. The merger product has collapsed into a black hole, which would have been, give or take, 2.7 solar masses. So, which would be sort of in the mass gap. So indeed, we should be careful about this. Alan is absolutely right. What we really mean is, by the mass gap, that whether or not in emerging binary, one of the companions would have a mass in one or the other mass gap. Yes, please. So at when the stars are born, right, when we're looking at young stars, observationally, the mass distribution seems to be roughly flat. So if you could write down the mass ratio Q as, let's say, the mass of the smaller object divided by the mass of the larger object. So it looks like, P of Q is roughly 1, meaning it's a roughly flat distribution independent of Q. What that may be surprising to you, because what that's telling you is that the secondary in an initial stellar binary is not independently drawn from the initial mass function. This distribution tells you the vast majority of stars have low masses. So if I randomly pick, if I take a binary, a stellar binary, and I happen to have picked a primary that has 60 solar masses, if I drew the secondary independently from the IMF, most of my secondaries would be, 0.5, 1, 2 solar masses, right? In fact, this is telling you that half of my secondaries will be also very massive 30 plus solar mass stars. So that's an observational statement. Why it is? Well, this obviously has to do with something with, with how these binaries are actually formed, and fundamentally it could be down to either the process of star formation itself, the fragmentation of a giant molecular cloud and the feedback associated with star formation. It could have something to do with dynamical interactions very early in during star formation, right? So maybe even when you have pre-main sequence stars, you're really forming a whole bunch of them out of a single molecular cloud. They're moving around, they're dynamically interacting. Some of them might be merging, some of them might be exchanging in binaries, and that's why you end up with this distribution. It could have something to do with accretion, because, for instance, if you form a binary with a sufficiently extreme mass ratio, you have a massive object here and a relatively low mass companion. The low mass companion is doing most of the motion, just Kepler's law, right? The high mass thing is sitting there, and what it means is you still have a lot of gas around. It's this low mass guy that's moving around that's going to be sweeping up most of that gas. So it's going to grow while the high mass guy basically stays at the same mass, because the supply of gas is being shut off by the small thing orbiting around. And so maybe that's what leads the binaries to move towards roughly equal masses. There have been suggestions that it's all of the things mentioned above, or maybe some combinations of them. They all roughly seem to work. I don't think we actually know which one of those is the main contributor to explaining these kinds of observational statements. But these are observational statements. By the way, the other one I should say is initially P of A is something like 1 over A. This is called Öpik's law. Öpik was an Estonian astronomer who published a paper in I think something like the Tartu Observatory News that in 1924 that probably As far as I know, nobody has ever actually seen the paper, but everybody cites it. So it's because he was possibly the first guy to have said that the initial separation distribution in binaries is uniform in the log. That's actually a very important statement for us, because if we do care about closed binaries, the statement is actually, there are plenty of those, right? You might think, well, you know, how many binaries could I form? There are only a few stellar radii in separation. These things must be extremely rare, given that binaries have a range of separations initially ranging from a few stellar radii to thousands of stellar radii. But actually it turns out that, you know, between a few and a few tens of stellar radii, well, you've got, you know, 20% of your binaries sitting there, right? They're not that, tight binaries aren't all that rare information, and it's all because of this flattened log distribution. Oh. If there is somebody who actually knows how to correctly pronounce this, please let me know. I pronounce it as epic. Okay, or Epic's law. I think it's 1924, or close enough. Okay. By the way, some of the observational evidence for this, if you are looking for the right papers, Uksane et al., 2012, I think it was in Science. There's a couple of very nice papers by Max Moe and Roseanne DiStefano. I'm not going to pretend to remember the year, but it's, you know, 2016-ish, so it's fairly recent. They had a couple of papers basically sort of discussing the observational evidence for these kinds of distributions, particularly in the context of massive stars, as well as discussing things like the presence of triples, quadruples, and so on, which massive stars are very fond of creating. Okay, so let me just finish with this review of what LIGO has seen, and then I realize that in 10 minutes we'd better go and get some lunch. I still have 10 minutes, right? Okay, perfect. Okay, so, and then we will, I think that's going to put us in a good place to start tomorrow morning discussing the actual formation channels, now that we've discussed some of the observational evidence and some of the, let's say, background for what stars and binaries look like. Okay, so we have 1 binary star event, 6 binary black hole events. They range from something like 10 plus 10 solar masses to something like 30 plus 30 solar masses. I write them as equal masses. We don't actually know that they're equal masses. The mass ratio is not particularly well measured. Some of them could be as extreme as 3 to 1 or 4 to 1 mass ratios, but they're all consistent with being equal masses. So I'm just going to, for simplicity, pretend for now that they are, you know, equal, or at least, you know, with mass ratios no more extreme than about 2 to 1. The other thing that's worth noting is that all of them are, at least for these events, are at redshifts of 0.1 to 0.2. So that's about 500, I need some space, megaparsecs to 1 gigaparsec. It's not exactly right. Some of them might be a little bit closer than 500 megaparsec. Some of them, the posterior and the distance extends a bit beyond 1 gigaparsec, but order of magnitude. This is sort of the local universe we're able to probe. In principle, for something like GW 170817, this 30 plus 30 solar mass binary, if it were really optimally oriented, optimally located, LIGO might have just about seen it to a redshift of 0.4 or 0.5, but the vast majority, at least given the current sensitivity, the vast majority of the sources we would expect to see at these relatively low redshifts. Of course, at very low redshifts, you have much less of the universe available to you, right? I mean, at low redshifts, you can think of redshifts as a kind of proxy for distance. They're roughly proportional to each other, right? That's Hubble's law. And so, of course, the volume goes as distance cubed, so you don't necessarily expect to see lots of binaries coming from a redshift of 0.0001. But at high redshift, you're being hit by the decrease in LIGO sensitivity. I said that optimally oriented, optimally located binaries might be seen at redshift of 0.5, but of course, if your binary isn't optimally located and optimally oriented, the horizon distance to it decreases, and so that means that you're really talking about seeing things in the relatively nearby universe. That's actually helpful in a way because we think that probably in this between redshift of 0.1 and 0.2 not much has changed, and so whatever statements we're going to make about the LIGO and Virgo sources, about their rates, intrinsic merger rates, and their mass distribution are valid in the sense of assuming that things are about the same at all of the redshifts to which the detectors are sensitive. That will not be the case going forward. So for instance, some of the assumptions that LIGO data analysts have made in the past, that everywhere in the universe, part of the universe observable by the detectors, the mass distribution of binary black holes is the same, and their intrinsic merger rate per unit source time, per unit co-moving volume is the same. Those assumptions will no longer hold because we expect from models of binary evolution that things will change as a function of redshift. The most obvious reason why they change is that the star formation rate changes quite significantly as a function of redshift. The star formation rate at redshift 2 was more than a factor of 10 higher than it is today. So you might imagine that therefore the binary merger rate would also be very different at different redshifts. And so that's something that will have to be accounted for in the future interpretation of gravitational wave events. But for now, this makes our life somewhat simple. Another thing that's worth noticing is that something about the spins. The spins are low, at least the spin component in the direction of the orbital angular momentum appears to be low, or at least the total spin component in the direction, total mass weighted spin component in the direction of the orbital angular momentum is low, right? So this chi effective parameter, have people actually talked about this already? This afternoon. All right. So, okay, I'm not going to even define then chi effective because Alan will talk about this afternoon, but chi effective, think of this as a kind of mass weighted spin in the direction of the orbital angular momentum. That's the spin component that LIGO is best able to measure, and LIGO and Virgo are best able to measure. And this parameter for all events so far is less than about 0.2, and for only one event it's inconsistent with being 0. Maybe. So, okay, these are the events I know about. Of course, there may be people in the audience who know more than I do about these things, but the events I know about, this is the case. And so that the fact that there's one event where it seems to be marginally consistent with being 0 suggests that at least some black holes do have non-zero spin. At the same time, this tells us that the picture is already pretty clear that it's not the case, for example, that all black holes have maximal spins of chi equals 1 aligned with the orbital angular momentum. If that were the case, that's inconsistent with this picture, with the existing observations. Okay. What else do we need to know about the data? Maybe there's one more thing that's worth saying, and this is not specifically about LIGO data, but it's about the other best way we have of measuring black holes, and these are black hole X-ray binaries. So black hole X-ray binaries are binaries where you have one companion, which is a black hole, and another companion, which is some kind of a non-degenerate star, so a massive star of some sort that's orbiting this black hole. In some cases, so-called low-mass X-ray binaries are typically fed by just mass flow from the companion, where the companion is being tidally stripped by the black hole, right? So the star gets tidally extended by the presence of the black hole. For people in this field, this is called Roche-Loeb overflow. I'll discuss more about that tomorrow. But mass is being transferred onto the black hole. In other cases, you just have winds coming off of the star. Um, this is particularly true for more massive companions. They are not overflowing the Roche lobe yet, but they are having significant winds, and some of those winds end up on the black hole just through simple Bondi-Hoyle accretion. In either case, you can try to measure the parameters of the binary and measure the mass of the black hole, and we know that black hole X-ray binaries, at least certainly the ones in the Milky Way, point to the fact that A, the black hole has a maximal mass of about 15 solar masses in the Milky Way. Let me make a little bit more space. Mass, black hole mass, is less than or equal to 15 solar masses in Milky Way. This is the most massive one we have a good measurement of in the Milky Way is Cygnus X1. It doesn't mean that more massive things don't exist. It just means we haven't seen them. We only have about 15 objects with well-measured masses. There has been some evidence of maybe things that are getting a lot more massive in other galaxies. So IC10X1, NGC300X1. These are black holes that might have masses of 25 or 30 solar masses. But actually, there are some issues with the measurements. So really, I would say that this really is the one that we can be truly confident about as the mass record holder. The second thing is black hole spins in high mass X-ray binaries appear to be high. And by high, I mean that chi is of order 0.9 or greater. This is based on really about 3 systems where there are different ways of measuring black hole spins that agree on the answer. Most of the ways, by the way, of measuring black hole spins boil down to looking at the accretion disk around the black hole. You can imagine at the simplest sort of explanation of how you might go about measuring the spin is the following. You know that the radius of the innermost stable circular orbit depends on the black hole spin. So if you have a high, very rapidly spinning black hole, you can get an ISCO radius for a prograde disk going down to r equals m, whereas for a non-spinning Schwarzschild black hole, it's going to be at r equals 6m. So of course, where the material is in the disk changes the temperature of the disk and changes the emission profile from the disk. And so by looking at different features of the disk emission, you might assume that there should be some way of figuring out what the shape of the disk is and where the innermost radius of the disk is, which you assume is at or near the ISCO. And that's what people have done. There are a couple of different ways of doing this. There is something called sort of reflection mapping with K-alpha iron lines. There is something called continuum flux measurements. I'm not going to go into details of those beyond pointing out that actually these two things don't quite agree. Out of about 6 sources or 7 sources where you have measurements from both channels, 2 give you measurements that are inconsistent by more than 3 sigma. So you might kind of worry about this a little bit. Some people seem to not worry about this, so I'm not entirely sure why. I think at the very least it's telling you there are significant systematics in the methods, and so you shouldn't trust the claimed error bars, because clearly you should not be finding that out of 7 events or 7 systems, 2 are more than 3 sigma apart. But to the extent that you believe these measurements, there are a few systems that have these quite high spins, and these are probably the closest systems to the progenitors of what LIGO might see, at least at first glance. Because we're talking about binaries that consist of, let's say, a 10 or 15 solar mass black hole and maybe a 15, 20, 30 solar mass companion massive star going around that might eventually make another black hole. So wouldn't these be the natural progenitors of LIGO systems? And if so, how come LIGO is measuring these low spins, whereas these things seem to have high spins? So that's another one of these puzzles that we need to somehow understand, and we will probably talk about tomorrow, given that we're at an end. But you got a question? Okay. So I'm going to stop here, but are there any more questions? Yes, please. No, this is the chi of that individual black hole. But so chi is just the angular momentum in units of mass squared. So it's the dimensionless angular momentum, dimensionless spin angular momentum of the black hole. This can have a value. Okay, the absolute value of chi is between 0 for a Schwarzschild black hole and 1 for a maximally spinning Kerr black hole. If you had two equal mass black holes, both with spins, maximal spins pointing in the direction of the orbit, the effective chi would also be 1. If you have two equal mass black holes with one of them being maximally spinning and the other one, let's say, being non-spinning altogether, the effective chi would be 0.5. If that first maximally spinning one pointed in the orbital angular momentum direction. So even if these things were to go on to make two black holes with roughly equal masses, the fact that the first one seems to have a nearly maximal spin would suggest that your chi effective should be 0.5-ish. And okay, of course, if the second one somehow ends up with a maximal spin anti-aligned with the first one, yes, you could get a chi effective of 0, but that's a very tricky configuration to contrive. So let's say at lowest order, this seems like there might be some kind of a discrepancy here, something that's worth understanding. And we'll chat more about how these various channels might explain this discrepancy or might not tomorrow. Thanks.